Alice, Bob, and Eve explain quantum state tomography.
I'm trying to create a complete 3D model of this vase, but I can only capture 2D images from different perspectives.
What you're doing reminds me of quantum state tomography, a crucial technique in quantum computing.
Quantum state tomography is fascinating. It's how we figure out what quantum state we've actually created in our experiments.
How does photographing my vase relate to quantum computing?
In quantum mechanics, we can't directly observe a quantum state without disturbing it. It's like how you can't see the entire vase at once. You can only take 2D projections from different angles.
When you measure a quantum system, you collapse its state, getting just one classical result. It's like taking just one photo that shows only one side of the vase.
So how do you determine the full quantum state?
We prepare many identical copies of the quantum state, then perform different measurements on each copy. Each measurement gives us a partial view of the state, like your photos from different angles.
Just as you'll combine these photos to reconstruct the 3D vase, quantum state tomography combines multiple measurement results to reconstruct the quantum state.
I need enough different angles to capture the vase's full structure. How many measurements do you need for a quantum state?
That grows exponentially with the number of qubits. For a single qubit, we need at least 3 different measurement settings, typically along the X, Y, and Z axes of the block sphere.
Think of a single qubit as a ball. We need to measure its projection onto each of the 3 perpendicular axes to fully reconstruct its position.
And for multiple qubits?
For n qubits, we need at least 3 to the power of n different measurement settings. That's why tomography becomes extremely challenging for large quantum systems.
It's like if you had to photograph not just one vase, but a complex arrangement of many objects from all possible angles. The number of required photos would explode.
That sounds incredibly resource-intensive.
It is. That's why researchers have developed more efficient approaches like compressed sensing tomography or shadow tomography that require fewer measurements for approximate reconstruction.
There's also an important mathematical step. From all these measurements, we use techniques like maximum likelihood estimation to find the quantum state that best explains all our observations.
So my camera is like your measurement device, taking partial snapshots of something I can never see all at once.
Exactly. And just as your final 3D model helps you understand the vase's properties, reconstructing the quantum state helps us verify our quantum operations and debug quantum algorithms.
It's essential for benchmarking quantum computers, characterizing noise, and ensuring our quantum gates are working as intended.
Next time I reconstruct a 3D model from my photos, I'll remember I'm doing something conceptually similar to what quantum physicists do to understand the invisible quantum world.